Hello, my name is Santos Cordills, and the study I'm going to be presenting today is titled The Impact of Biostatistics on Hazard Characterization Using In Vitro Developmental Neurotoxicity Assays. This is a study that was published in 2023 and comes out of Germany. The data that this study examines are called benchmark concentrations, or BMC for short. These benchmark concentrations are used to evaluate the toxicity of in vitro data sets, and they're determined through data modeling as a result of many various statistical decisions and assumptions. Oftentimes, the person who is conducting the experiment is performing the data analysis instead of an experienced biostatistician. So, in this circumstance, when the experimenter is performing the data analysis using statistical software, they might not be aware of certain settings or other statistical assumptions that come with certain tests. Differences in statistical assumptions could change the classification of developmentally neurotoxic substances, which can have serious health implications. So, understanding this problem really is important. Any good statistician knows that the key to a successful study is having a good experimental design. So, before an experiment even can take place, our authors say that there are a few key statistical decisions that need to be made first. The first is whether to replicate distribution and the choice of a parameter for analysis. So this means when it comes to our descriptive statistics, are we going to use the median as a location parameter, or should we use the mean? This is going to depend if our distribution is symmetric, if there's data outliers, or if there are some like biases. And so we'll have to decide that before the study. The next is response data normalization. This just means should we, normalize all of our data to a control, or is there evidence, for not normalizing the data? Next, we need to decide the regression model. Do we want a flexible model that can account for a lot of data, or do we want to use several different models and select the best model based on a goodness of fit test? Or do we want to come up with some sort of like average model that can explain everything? The next key statistical decision that needs to be made is the uncertainty of the estimation. This is just the alpha level, the confidence level. Usually when we're performing statistical analyses, we'll use an alpha level of 0.05 or 0.01. Depending on who's carrying out the analysis and what software they're using, this value may be predetermined or assumed, or the person performing the analysis might not know how to change these levels. So this is an important decision to make before performing the analysis and even before performing the experiment. And then the last decision to make is the benchmark response. This is just, what level, how much deviation from the control does there need to be before we say that we have some sort of like significant difference. So as a big overview, this is what our study is looking to do. We're looking at the experimental data, the data about the, distribution between the different wells, the different models and measurements, and can differences in certain statistical assumptions translate into different classifications for neurotoxic substances. So generally, when we perform a statistical analysis to examine the benchmark concentrations, we'll be able to use that analysis to sort of decide if we've come across a substance that is neurotoxic or is not neurotoxic. And so based on those values, an automated system will pick out specific hits or unspecific hits, or not identify any hits at all. So this study is really looking to see how different assumptions and statistics might affect the detection of neurotoxic substances out of a data set. Furthermore, we want to see if these different assumptions affect the assay performance in terms of specificity, sensitivity, and accuracy. So the hypothesis of the study is that the selection of common biostatistical concentration response methods do not affect the performance of a neurotoxin in vitro battery test. Our study is looking to see really if these sort of like biostatistical methods affect what we classify as neurotoxic or not, and based on what we already know about the neurotoxicity of these certain substances. The authors of our study have developed a decision tree for hazard classification of neurotoxic substances, and the hazards can be classified into 5 categories: either no hit, unspecific hit, borderline hit, specific hit, or not identified. And the difference really is between the separation of effects at the specific endpoint versus the effect of the substance on the cell health. So we want to really separate those two effects from each other. The authors have developed this decision tree for hazard classification, and it's sort of a standard protocol for evaluating and analyzing data, so that people who maybe are not like the most statistically savvy can sort of have a procedure to follow, a protocol to follow when it comes to analyzing this type of data. Depending on sort of what tests are able to be carried out and what information is available, the hazard will be classified in either a certain category, or the decision tree will call for an expert judgment to come in and actually look at the data themselves and decide what sort of hazard this would classify as. Here are the different data evaluation methods that are going to be changed as sort of like our experimental variable throughout this analysis. Some of the different methods are replicate mean, control normalized, the LL3 regression model, the delta method, bootstrapping, and also the standard protocol that was developed by the authors to systematically analyze the data via decisions through a decision tree. Here we can see the impact of the methodological changes in the data evaluation of the benchmark concentration estimation. As you can see, in A, there's an R-squared value of 0.81, and in B, there's R-squared of only 0.3. In C, there's an R-squared of 0.59, and in D, there's an R-squared of 0.85. This is telling us that the model averaging is giving us the best fit of the data. Here we can see more of the impact of the methodological changes on the benchmark concentration lower limit. And so this box and whisker plot is showing us the ratio between the benchmark concentration lower limit for each of the different methodologies, statistical methodologies, versus the benchmark concentration using the standard protocol. So for some of the methods like replicate mean, we can see that the interquartile range is pretty much centered at 1, meaning that there is no difference between that ratio. This can be contrasted with looking at the delta method, which shows an interquartile range that goes past 10, meaning that the change is 10 times greater than the control, which is really a significant difference. Here we can see the number of classification changes in response to changes to the standard data evaluation protocol. So you can see here, like when in the first double bar for replicate mean, we see about a 2.94% change in certain classifications. So 1% of the new change might be specific hit that wasn't previously identified as specific hit, and so on. We can see that for the LL3 regression model, there's a 45.87% change. So that is a huge difference in the number of data points that get classified as neurotoxic or not based on one statistical assumption. Here we can see all of the different data evaluation methodologies and how they affect specificity, sensitivity, and accuracy. So we can see certain models in specificity, like model averaging and summary by mean, are giving us a lower specificity combined with sensitivity, and we get accuracy levels. And we can see from graph C that standard protocol actually gives us the most accurate testing compared to all of the other data evaluation protocols that are listed. The big conclusion that can be drawn from this study is that statistical decisions that seem minor can actually have significant impact in hazard identification and classification. The authors believe that this could be extrapolated further in many fields that rely on statistical analyses, that these minor statistical assumptions really do have significant impact in your results. And so somebody experienced with statistics should be evaluating all these statistics, or maybe we need to see that our experimenters have more statistical training and more robust experiment design. Standard protocol for the automated data evaluation helps to sort of balance all of the statistical assumptions without overcomplicating the regression analysis. And that's why the standard protocol gave the most accurate testing out of all the methodologies. So in the time that our experimenters maybe don't have the best understanding of statistics, at least there's a sort of automated standard protocol that biostatisticians can fall back on to analyze their data. Thank you so much for allowing me to present.